Ready?
Okay, everybody. This is Richard Shaughnessy visiting from Rochester Institute of Technology. I've been managing for 10 years now. We're both members of the LIGO scientific collaboration. I forgot to ask your history. I know you did a postdoc.
So I degree with Kip, worked with Vicky, was at Penn State for a while, was at Milwaukee, and now I'm at Rochester.
And so he's going to talk about dynamics of spins in precessing binary black holes, and just to deflect some heat from our guests today. If you have heard anything about rumors, please don't put them on the hot seat and make him have to answer uncomfortable questions while he's on camera.
Yes, I am not speaking as a member of the LIGO scientific collaboration. I'm not speaking about data. I'm not speaking about parameter estimation. I'm just speaking about astrophysical and strong field GR theory, about work that I think is really exciting that's happened over the last year, that's theoretical, by myself and particularly Davide Gerosa, whose website I'm highlighting here. I highly recommend that you go to it. I'll show you some movies at the end. And also my more senior colleagues, Mike Hesden, Emanuele Berti, and Ulis Berhaki, and also Daniela Trefiro, who's done some really interesting work on parameter estimation. In other words, converting these theoretical ideas that I'm about to describe into something that will be useful for interpreting LIGO data when it's available. So this is going to be insight on an old problem. How do binaries consisting of two black holes gradually, and I will do the interpretive dance, gradually spiral in through the emission of gravitational waves, approach one another, and coalesce? That last part is hard and requires detailed simulation, which is beyond the scope of this talk. I'm going to talk about something you can do analytically. And in fact, many of the calculations that I'm going to be described can be done with basic vector algebra by an undergraduate and do not require any detailed knowledge of relativity. In fact, when I say vector algebra, I mean we're not even doing calculus in many cases. This solution is extremely easy to understand. And I'll try to convey, despite the simplicity of the operational mechanisms that allowed us to define the solution, it provides a new perspective which allows us to understand something that we thought previously was very complicated. The evolution of a moderately high dimensional nonlinear ordinary differential equation turns out to be something that's surprisingly simple and solvable. So I have to begin with some motivation, particularly given the time of year and what's going on, about the dawn of gravitational wave astronomy, which I think all of you have heard before, but nonetheless I feel it's a wonderful time to remind ourselves of why it's such an exciting time. I'll then describe why I think it's not a waste of time to really think about precessing bicolor binaries, why I think that there's a good astrophysical rationale for spending time to consider the gravitational waves they produce as a plausible detection candidate for gravitational waves in the future. I know how the sausage is made. I will tell you how the sausage is made. I'm not going to say that everything that goes into these calculations that motivate why it's interesting ensure that it must be interesting, but I hope I'll convey some of the excitement of that field to you. I'll then describe our solution and some implications it has for things that previously people thought they understood but didn't. I'll describe how we can use this solution practically. It's not just some neat pen and paper solution that, yeah, great, you can solve something, but you can simulate it anyway. But it's something that provides new qualitative insight that in particular is useful for extracting information from gravitational wave data, synthetic gravitational wave data. And I'll describe some future directions that we've been pursuing. So why study gravitational waves? Well, I think that's probably all I have to do for this audience. But just to make it clear, gravitational waves are like electromagnetic waves. If you wiggle a charge, then you're producing an electromagnetic wave that's propagated at the speed of light. They're screening. So electromagnetic charges exist of two signs. So I can't produce an arbitrarily large electrostatic charge. So that limits our signal. And it's strongly coupled. So while it's easy to make electromagnetic waves, it's also easy to obscure. And that means that they're fascinatingly useful. I mean, we see with them. But it's difficult to reach inside some things that we might want to see inside. Conversely, as you all know, there's only one side of gravitational charge. So it's easy to make very large sources for gravity, the Earth. You're not a pancake. Gravity is very weak. And therefore, that means that because the coupling constant is very small, while it's very difficult to make gravitational waves, they're almost impossible to obscure. They travel through everything from anything that's ever made them. And that means that they provide an unobscured probe of some of the most violent and energetic processes in the universe. We know they exist. Again, I think this audience knows that. There have been observations of neutron stars in pairs. One of them is spinning and sending up pulses, which reach us from our happy radio telescope on the ground. By carefully timing the arrival time of these pulses, we can tell not only that there is a neutron star and it's spinning, but also that it's moving towards us and away. Towards us and away, just by the change in time between the arrival time of the pulses. So we know it's in a binary. And by very carefully timing the arrival time of these pulses, we can figure out that it's not only in a binary, but that binary is changing shape and shrinking in particular. And that means, that's a fascinating thing. What's very fascinating, someone got a Nobel Prize for it, two people in fact, is that we know that it's emitting energy to gravitational waves. Because the rate of change of decrease is precisely consistent with what GR would predict, given that we know what the two components are because of this timing that we've done of the orbit already. So we know they exist. And moreover, this thing tells us, this same object tells us something else. This object is in such a tight orbit that we know not only is it emitting gravitational waves now, but it's going to continue emitting gravitational waves for a while, but not for an infinite amount of time. It will, in fact, in the relatively near future, compared to the age of the universe, it will coalesce. Its orbit will shrink, contract, shrink, contract, shrink, contract, and eventually they will come into contact and merge. So therefore, this object not only tells us about the existence of gravitational waves, but points to the viability of a strategy for looking for gravitational waves emitted just prior to coalescence when the objects are moving very rapidly, close to the speed of light, and the binary is in a very high frequency, hundreds of hertz. And this is precisely what detectors like LIGO were built to look for. And in fact, we're in a regime where the detectors that are operating soon, so this is design sensitivity, combined with how often we think these mergers occur based solely on looking up at things that we know exist in our own galaxy, and how many galaxies are like our own, you can be pretty confident that in the relatively near future, we're going to detect gravitational waves from the coalescence of binary neutron stars. Now, when I say very near future, I mean very, very, very near future. So if you just want to look at binary neutron stars, this is an operations plan that the LSE has published for how it, roughly speaking, it plans on operating. It expects future operations to work in the present and future, combining the range, what you might expect for the number of detections given the significant uncertainty in the event rate. I just quoted one number. There's some uncertainty in the pulsar luminosity function and Poisson statistics. And you can see that this number, there's a range. This is ridiculously pessimistic. So if you take something closer to the more optimistic number that you see here, you can see that relatively soon we'll have a pretty good chance of detecting several binary neutron stars. Now, that's just binary neutron stars. You'll notice the title of my talk did not involve binary neutron stars. Why? Well, LIGO can detect a lot of things beyond just binary neutron stars. I mean, binary neutron stars is they're a wonderful system. We know they exist. But LIGO is sensitive to things much, much farther away. So this is a plot of advanced LIGO's, the maximum redshift to which you could detect a source with advanced LIGO, assuming 2 interferometer coincidence, so you're limited by the second most sensitive interferometer, operating at design sensitivity. So this is not the things that exist now, as a function of the observed total mass, and that means that I'm taking into account the fact that there's redshift of the source. And you'll notice that this is not a small redshift. This is a significant distance, maybe not z equals 13 for those of you who do cosmology, but for those of us who are interested in the evolution of the relatively recent universe, this is seeing sources relatively far away. There's a lot out there between here and z of 1 or 2. And can we be sure that binary neutron stars are all that's out there? Can we be sure that there aren't any sources of even these masses? there's been a long theoretical tradition exploring the possibility of things other than binary neutron stars as candidate sources for LIGO. So this comes largely in two flavors. The possibility that you'll get binary black holes, and this is making a sausage. I'm about to make sausage. There are aggressive theoretical assumptions that are about to be discussed. They are aggressive. Before I begin, I will highlight the fact that the rate could be very, very high if we're optimistic, or very, very low if we're pessimistic. And I'll summarize what goes into the upper and lower limits at the end. But let's imagine for a second, what would it take to make binary black holes? Well, one way would be put a bunch of stars in an interacting environment, shake it, because they interact. The black holes segregate down to the center. They start interacting more and more rapidly through the classic Spitzer instability. And you'll rapidly produce lots of binary interactions of black holes. This has been explored for years and years and years and years and years. And there's been some recent analyses that have been refining the cluster model, both N-body and this is Razio's Fokker-Planck group, to try to show that taking into account everything that they know how to take into account, binary interactions, kicks, evolution, you still predict, and these predictions have been in this level for quite some time, event rates of tens in the low end, to hundreds in the usual end, to thousands in the high end for advanced LIGO per year at design sensitivity. To get the highest rates, you have to do things that are even more aggressive than appear in this paper. I'll discuss their figure in a second, where you have to use low metallicity star-forming environments, and you have to assume that all stars form in clusters somewhere during their lifetime. This is something that, yeah, people like me have said before. It's a possibility, and it's possible that that doesn't happen, in which case you're on the lower end. But putting this sort of idea forward, roughly speaking, you expect, oh, you can't quite see that. There's a redshift axis on the bottom. From 0 to 2. And this is where you would expect to detect LIGO sources in the relatively local universe. Depending on the composition of the sources, with solar metallicity or subsolar metallicity, it's possible that LIGO could be detecting these sources at this rates with sources of chirp mass from 10 to 20 solar masses, where chirp mass is a particular combination of masses that enters naturally into calculations of in-spiral. I think that is the canonical chirp mass. I do not recall off the top of my head why they put that in there. I just cut it out from their figure. I can pull it up if you'd like to see afterward. So the other piece of sausage that you could use is something that I've worked a little bit more closely on, is binary black holes formed in the field from isolated stellar evolution. Or isolated, meaning they form in pairs or maybe triplets, but usually pairs. And as they evolve, they become larger. And this brings them into closer contact, because they're physically larger, with their companions. And therefore, they can transfer mass back and forth. This process is complicated, involving enormous amounts of physics that we don't understand, and for which particularly in this mass region, there is no useful source of data to calibrate during these epochs, to be very blunt. It would be nice if things like Gaia and additional observations of transients would allow us to calibrate our understanding of binary evolution in general. It would be very nice if we had a greater understanding of how supernovae work, which we don't. So take everything that I'm going to say both on the previous side and this side with a grain of salt that involves massive uncertainties where there's a great deal of debate in the community. That being said, putting in a range of models that account for some of the theoretical uncertainty, you can get a prediction for how many events you would expect to see in the next 3 months. This is a number of events. And this is an analysis based on a paper I wrote. So yes, this is something I technically should stand behind. And you can throw tomatoes at me at the end. And this is another paper that's going to come out soon, which says more or less the same thing. What we're saying is that unless you do aggressive things, from the isolated stellar evolution, you would expect to see a lot of binary black holes, a lot of detections from the first generation instruments starting very soon. And you would expect these to be dominated not by low mass objects, because we know how many neutron stars there are, but by relatively high mass objects. And this is just, we've been saying this, I gave a talk on this 3 years ago at a conference. This is basically the same sort of slides. The analysis has not changed. We're just refining our way of presenting it clearly. And this is a post-processing of that previous result. So this is a more optimistic model, and this is a more pessimistic analysis of the same model. So this is what you would expect to see in the first generation in an optimistic scenario and a more pessimistic scenario, and in the second observing run. Yes, this is Stephen Citadel 2015. Yeah, this is a published reanalysis of some work that Chris Belczynski and Mikhail Dominik led. So this is all published. Oh yeah, can we lower this down just a little bit? Oh, that's fantastic. And oh no. I'm just going to stand here and hold it. Yeah, this is published. So I am now I didn't actually write this paper, but I believe they didn't screw up their interpretation of our results. So therefore, I must say that ridiculous as these numbers seem, they are consistent with what has been previously claimed by people, including me.
What's the spike amount? Is that neutron source?
This is neutron. OK, so I haven't talked about the figure on the right. So the figure on the right is the event rate per unit volume that you predict as a function of for LIGO to detect. And this is kind of a strange way of representing things. So rather than to express it as a detected number, we take the detected number and we divide by the volume to which we're sensitive. So we get an effective event rate. So it's the same sort of information that you see here. And then we bin by the observed mass, the redshifted mass. And so these are binary neutron stars. And these are binary black holes. And this is where we expect, using the same procedure based on observed masses, the upper limits from advanced LIGO and Virgo operating at 1 year at design sensitivity. So this is not anything that's attainable now. But you see that if in a relatively short period of time I'm going to look really bad, or I'm going to be a very, very happy person. So I'm going to be hiding for the next year. No breaks.
Does the table on the left also refer to 1 year design sensitivity?
No, this is actually a prediction for specifically 01. So this is a prediction for the next 3 months.
Basically the next, but then what was the corresponding prediction for the last completed science?
If I remember, it was just under, because the sensitivities increased pretty dramatically. I would have to check if they reanalyzed ER8.
Has the sensitivity increased differentially for more massive binaries with respect to the double?
Very much so. There's a certain, I mean, in this MASH regime in particular, there's a significant increase in sensitivity. And this is, well, for one, the searches are better. We do a better job at searching to high mass. I mean, do you want to answer this? Yeah. I mean, we're looking at things that have, you get a lot of information at, below 30 hertz, whereas you didn't really have that before. Below 40 hertz.
So the overall spectrum is only like that,
But below frequency end is open.
Yeah. So it's a really exciting time for those of us who would like to look for the unexpected. And to highlight this, that I'm not going to say that we can, now, this is the weasel time. I've got the sausage. I can always change the sausage to make this number small. So I still have an out. But I'd have to work pretty hard, and I'd look pretty bad if I picked the one model out of all the models that didn't work. And most calculations that we do predict many detections of binary black holes. And this is largely on physical grounds, based on the fact that we think that massive black holes don't receive ridiculously high kicks, and that you make them. Yes?
Can you say something about how far away we are right now from design sensitivity? What is the sensitivity now as compared to what the full?
I think right now our BNS range is about 70, and where the target is 220. Yeah, we're close.
again, with ENS, with a broadband signal, that's kind of measured in higher sensitivity. If you were looking specifically for, say, 200 solar panels, you might find much better. Quantifying this source.
Yeah, and again, if I was free to talk about things I've seen in LIGO, I know I've seen things in LIGO that have made this comparison, but I'm not talking as a LIGO person, so I can't show you the things that I've seen in confidence. But you can take what he just said as being true. Now, why is this important? Because okay, great, you see this thing, but it's a ridiculously short signal. What possible information could you get out of it? Well, one of the things that I hope that we will be able to get out of it is information about how the heck they formed. And you might think, well, this is a ridiculously short signal, and you're going to see the mass. But you have both of these models predict really high masses. And it's a really short signal, so OK, great. Now, can you tell them apart? And I think that there is some possibility, because you form these things in two very different ways. In one, you have an interacting environment. So they basically come together however they come together. Their spins are in some arbitrary orientation. So as long as black holes are born with some spin, you'll have relatively large spins in arbitrary orientations producing a complicated signal. In the other scenario, you'll have supernova kicks that happen iteratively and very gradually change the misalignment of the orbit. Slowly. And therefore, you expect that there'll be some relative misalignment and some total misalignment with the orbital angular momentum that will provide a clue as to, ideally, the formation order, which in fact is something that we think we may be able to actually have a handle on. We can tell which one is larger for reasons that I will hopefully have enough time to explain. And this is a conserved feature of the nonlinear dynamics, which is beautiful and wonderful and conserved for millions and millions of years. So that's fantastic that we'll be able to tell those things apart, despite the fact that it's precessing in a complicated way. But also the fact that it's simply that they're not very strongly misaligned would be a clue that this would be from a channel that was non-dynamical. So generally speaking, if you have large mass ratios with nearly aligned spins or moderate mass ratios, you would expect isolated evolution. Comparable masses with random spins ought to favor, based on the reading of the literature, cluster origin. So that's the usual rule of thumb people throw around. I'm going to have to hurry up. All right, so now the solution. So the first thing is, before I talk about the solution, I have to review how binaries spiral in, spiral in, and radiate. Their frequency increases, and then they coalesce. You know that. They produce a gravitational wave that increases in amplitude and decreases increases in frequency until it coalesces. You've seen that before. If one of the black holes and one of the components has a significant spin, then the binary doesn't just stay with its angular momenta aligned altogether, because there's a spin-orbit coupling. Now, the amount of effect that the spin has will depend on whether or not the orbital angular momentum and the spin angular momentum are comparable. If the orbital angular momentum dominates, who cares? The orbit basically stays non-precessing. These spins maybe do something crazy. Who cares? It's basically non-modulated. Gravitational wave signal is boring. However, once the two become comparable, then there start to become interesting effects that you can possibly have access to, specifically as follows. So the process of in-spiral, roughly speaking, keeps the direction of the total angular momentum conserved. However, as you radiate, you're shrinking your orbit, so your orbital angular momentum will decrease. Since this direction has to remain the same, and you have to conserve the direction of the total angular momentum, you will gradually flip the direction of the single spin, black hole spin, until it's eventually parallel, ideally, in the limit that you can continue this process indefinitely, until it is pointing along the direction of the total angular momentum originally. So in other words, the plane can, depending on the alignment of the initial spin, it could possibly even flip over. All the while, remember, there's also at the same time, so this is a secular effect, there's also the fact that due to spin-orbit coupling, the orbital angular momentum is also precessing. So what you see is the following. You see in the evolution is the following. It's going around, going around, going around. This is the orbital angular momentum, going around, going around, until it can potentially almost flip over. Now, the direction of strongest gravitational wave emission is along the orbital angular momentum, and the other one as well. So this means that you can get very strongly modulated emission from these precessing black hole binaries, even with one dynamically significant spin. So there's a lot of information there in spin precession. And this is just with one. So let's go to two. So these are the evolution equations that you need to solve for the gradual in-spiral of the orbit, which we parameterize by a parameter v, some differential equations for the spins, and a differential equation for the orbital angular momentum direction. And so you can solve this numerically, and that's been done for years. And that's what LIGO does for templates. And great, you can solve it. And People have thought this equation was chaotic. People have made lots of claims about the nature of the solutions to this equation over the years. But let's look at this equation and walk through it very slowly and systematically and say, I'm going to have to skip the next slide because it's technical. What properties does it have? Well, it has a natural timescale hierarchy. The orbit is fast. The precession rate is slower. The in-spiral rate is slower still. Second, except for the in-spiral time, the precession equations and the orbit equations preserve the direction of the total angular momentum. And it so happens they preserve another particular combination of the various spin angular momenta taken with inner product with the angular momentum direction. And I'm not going to be able to walk through this, but it comes from somewhere from the spin orbit and spin-spin Hamiltonians and orbit averaging. And now let's count. I'm going to go through this again quickly because I want to get to the meat of my talk, more fun stuff. If you go to a frame where L is along the z-axis, and you undo the precession of L, so you undo the fact that L is precessing, and you go to a frame where L is along the z-axis, and then you fix one of the spins to be in the xy plane, which you can always do. That leaves you only with a three-dimensional space that has to conserve the magnitude of the total angular momentum, J. And we have another conserved constant, psi. So the solution is, so the problem reduces to one dimension, it's integrable. The solution is basically linear vector algebra. Just saying, okay, we've got these, you've got this, you've got psi, you've got j. They have to be constant. What possible parameters do you have left? And then you have a Hamiltonian, which says you have a one-dimensional ordinary differential equation. So it's the solution, mechanically speaking, is very easy. You can then reconstruct in the inertial frame, knowing how the spins are evolving relative to one another, because you've solved that analytically. You then go to a frame where L is along the z-axis. You then put back in the fact that it's misaligned and precessing, and so the entire solution follows by quadrature. This is the solution that I've just described is valid on the precession timescale, but you can then put in spiral in a relatively straightforward fashion by calculating how much the total angular momentum will change as you shrink the orbital angular momentum. Because on average, L is doing something in some complicated way, but it's basically precessing around J. So on average, you know that the magnitude of J and L will change in a roughly geometric proportion. All right, so great, we have this analytic solution. So who cares? What insight does it give to us? So I think the first really interesting thing that I think this is helpful for is to explain a natural way of thinking about when we're not precessing and how the precessing spins evolve with time. In particular, so this is that coordinate system I was talking about where L is along the z-axis, S1 is in the xz plane, and S2 is in some other plane. So there's three angles that you can use to describe the phase space, theta 1, theta 2, and then some other angle that describes the relative orientation of S. So this is a plot of cosine theta 1 versus cosine theta 2. And it has a bunch of lines on it. The important part about these lines are not that they're lines. The important part about these is that these are fixed points of the evolution equations that occur when the spins are like this, coplanar, with one specific set of angles, which is red, or on the same side at two different angles, which is shown here in green. So there are two sets of fixed points. The Hamiltonian evolution, what it will do is it will tend to produce orbits that go around these fixed points. And so we're going to call the regions that surround these fixed points morphological basins because more or less the solution has the same structure. It's very close to a fixed point. And these two things are very different from each other. And so there must be some point at which you have a transformation from one to the other. So when does that occur? That occurs when, actually let me get to the next slide, when one of the the spins is aligned with L. Additionally, just moving into play? Oh, it's playing. Additionally, this representation provides an efficient way of understanding how the system evolves in such a way that it looks basically boring. We provided a set of solutions which respect the natural timescale hierarchy. We have J, the total angular momentum, and this conserved constant psi. In fact, not only is it conserved on the precession timescale, it's almost conserved during the in-spiral timescale. This is a plot of the phase space that you're allowed for a fixed set of mass and mass ratio. All of the points in this region are allowed configurations. And as you're spiraling inward, this is decreasing, but this quantity is basically unchanged. And these points here map directly back, for reasons that I'll explain in a bit. At asymptotic infinity, this maps into a distorted parallelogram here that you can, and that transformation you can work out analytically with just 2 lines of algebra.
So this one.
So these quantities at asymptotic infinity, you can figure out if you say, I know what J and psi are at some radius. You can then reconstruct the spin orientations at an arbitrarily large time in the past analytically without any. So if, for example, let's suppose you're worried about supermassive black hole recoil kicks. And you want to say, I know I get a very large kick if I have this particular spin orientation. And so you want to ask, what is the probability that I will get that spin orientation? And so you say, I need to have these misalignment angles. And then you evolve backward in time by pen and paper with this much space. And you get an expression that tells you these are the misalignment angles that I need to produce this type of recoil kick, for example. And so this is the sort of thing that we personally think, as a practical tool, is extremely valuable. The second thing I wanted to highlight was.
Minus again, though, conserved constants is coordinates. J squared is not conserved.
Sorry, conserved constants on the precession timescale, not on the in-spiral timescale. Yeah. I'm sorry for that. Yes. OK, I am going to have to race blindly through all the other wonderful stuff. But some of the other wonderful things that we find is that there are regions where remember how I said that there are these fixed points that you can be trapped near? And you're trapped near it if you're basically circulating around it and not going through large angle oscillations. So we have a definition for how to identify these fixed points and how to identify what we call phase boundaries, where we transition from one part of the phase space to another, which we can explain not merely in terms of this. So at any point on the evolution, we can say you're trapped near the fixed point or you're going through some large angle oscillation. And I'm not going to be able to talk about that. I have 5 minutes left. So I will talk about one cool result. One side effect of this analytic solution was that you would expect that if you had 2 spins that are aligned, they will stay aligned forever. Right? Symmetry. So if you have two binary black holes with perfectly aligned spins, the evolution equation would preserve that alignment if they spin up. And it would preserve that alignment if they're spin down. And it would preserve that alignment if the more massive object was spin down, but the less massive object was spin up. However, that is not true if you have the more massive object spin up and the less massive object spin down. It turns out that there is an instability to spin precession, which again, I think we ought to have appreciated before. And there's a very simple way of seeing that. For those of you who've read post-Newtonian papers before, there's this thing that Jeremy Schnittman discovered called post-Newtonian resonances. And you can plot basically where the fixed points are on this cosine theta 1, theta 2 plane. And there's a point where they detach, where this point here, this up-down configuration, is no longer along the curve of all the other fixed points. And that might lead you to think, wait a minute, maybe it's not a fixed point anymore. Maybe there's some sort of stability transition. And in fact, there is. There's a large range of radii for which, if you simulate it, it will just be unstable. And be unstable to large angle perturbations, large angle misalignment very, very rapidly. This means that if you have an in-spiral of a system in this configuration, it will be unstable. Now you might say, well, I don't care. Why would this ever be useful? If you're interpreting gravitational wave data, and the only model that you have involves aligned spins, and you, let's say, get a measurement that says, oh, I have evidence for a configuration with one spin up and one spin down, I can tell you that cannot happen. That is inconsistent with just our understanding of GR. And this also potentially has implications for producing electromagnetic transients from supermassive binary black hole in spiral. If you tend to align into a configuration where the more massive object is spin up and the less massive is spin down, you'll spiral inward. You'll align in this configuration. Then you'll have gravitational waves take over. Then bam, magic will happen. You get some EM transient, for example. So this is something that we think is potentially cool. I don't have enough time to talk about gravitational wave astronomy, except to tell you one simple fact. I told you these are natural coordinates. We can use any coordinates we want to parameterize the gravitational wave signal. And then we can say, let's see if we put in a synthetic signal, let's see if we can measure these parameters. We say we put in a signal with this value of j and this value of psi at some particular separation. So it is changing with time. And so this is a plot where we put in a signal of SNR20. And so this contour here is where that phase space boundary would be. And these colors, these stars denote where we put in signals. And these colors denote the posterior distribution in j and psi for each one of these different types of sources. And you can see that this is a relatively loud source. But even if we go to things that are almost face on, that I am going to show you here. So even if it's almost face on, if it's exactly face on, it's very hard. But if it's almost face on, we can pin it to this particular side of the phase space. We can be sure that it's near this fixed point and not near these fixed points. Why does that matter? Because, as I said, which fixed point you're near, whether or not you're like this, gives you a clue to the birth order. This is something I wasn't able to dwell on, but it's a fascinating fact that if you just do standard kinematic simulation of supernova kicks, this is this Newtonian physics. I'm going to put a kick on object 1, and I have a kick on object 2. What are the sort of misalignment angles I expect? Well, if you, depending on which one you kick first, you'll preferentially populate this area or this area. And that puts you in the regime of near one fixed point or near the other. And because we can identify which fixed point we're close to pretty reliably, this means, and this is a nonlinear two-spin effect, so it's cool the fact that we can identify it at all, as opposed, we're clearly having signatures of both spins here. So it's cool that we can measure it. But I think personally it's even more cool that a feature in the signal that was encoded hundreds of millions of years ago has been preserved robustly through a complicated nonlinear ordinary differential equation, the evolution of spin precession, in a way that allows us to, by looking at the signal right before it's about to coalesce, get a clue that you may disagree with. You may take with a grain of salt as to whether or not the interpretation is correct, but gives us a clue as to what was going on in the past, in the far distant past. And so the ability to exploit these conserved constants, and I'm going to skip this slide entirely, which just shows well, not entirely. This also is cool. The reason why these have this particular shape is because what we measure is this is a plot of the two natural modulation timescales. So roughly speaking, we're measuring the average precession rate. And that's why you get this elongated shape in this direction. And the extent in this direction is because there's another timescale in the problem. So roughly speaking, the fact that we have ellipsoidal contours with this shape means that we're measuring the average precession rate and this secondary timescale associated with the relative spin orientations changing. And it shows up very clearly as a result in our posterior distributions that we're going to look to explain and exploit more in the future. This is particularly the parameter estimation stuff I've shown you is very preliminary. It's not something that's been validated over a wide range of things. The analytic solution is, of course, exact. It works everywhere to the extent that post-Newtonian theory is valid. I think that both are going to be extremely useful to exploit the first gravitational wave detections in the near future. Many of them have also implications for the evolution of supermassive binary black holes. I think that we're going to be in a really interesting regime, whether or not you believe anything about the sausage factory. I think that LIGO is entering a regime where we will soon be able to challenge our understanding of the evolution of massive stars. And maybe there's nothing. And my ridiculous, overly optimistic predictions look overly optimistic. But at least we'll know, because LIGO can see things far away. And I'm personally optimistic that we'll be able to do quite a bit, both with LIGO, because it's going to detect something, and then we're going to get something bigger. And once you make something bigger, and we can see things regularly, binary neutron stars out to redshift of 2, then we're definitely going to find these things. But I'm pretty optimistic that even within the next few years, we'll be able to do fantastic things. And that hopefully will complement measurements from Gaia, LSST, and direct observations of stellar binaries to help us pin down our understanding of how massive binaries form. Thanks.
Time for some questions?
So the basis for your analytic solution went by pretty quickly.
Yeah, I was rushing because I saw the time was moving.
To what extent does it rely on variance?
Pretty heavily. So your concern is the fact that our timescale averaging isn't going to work late in spiral.
Well, I just want to understand
Everything that I have said relies entirely on orbit averaging and adiabatic invariance. And I skipped the derivation of the conserved constant, but the Hamiltonian that we're deriving this from involves, so this is the spin orbit and spin-spin Hamiltonian. This is the orbital separation vector. And to get, if you orbit average this Hamiltonian, so you can explicitly see the mechanics that I'm using, then you get a Hamiltonian that just depends on it literally is something times psi. Psi is the Hamiltonian. And since psi is the Hamiltonian, it's conserved. I mean, it's proportional to him. It's V, I don't remember what power V. 3 halves V to some power eta, and then there's some expression with psi. And so adiabatic invariance, all the classical mechanic tricks that you know are built in. Now, and we've seen issues with Kozai. Is probably why you're bringing that up. Is that okay? Okay. Just to understand the mechanics of it, there is a Hamiltonian. We orbit average the Hamiltonian to get a revised Hamiltonian, and then the revised Hamiltonian we because psi is a conserved constant, we're then basically done because it's conserved. So there's no other degrees of freedom to work with. But the orbit averaging is a critical step. Alternatively, and the way we originally derived this, we were orbit averaging the equations of motion. And so if you orbit average the equations of motion, which does the same thing, this becomes something which doesn't depend on the orbital separation anymore. But then the mechanics are the same. So it does all depend on adiabatic invariance.
Explain a little bit more what you mean by psi is a 2pn adiabatic invariant.
We don't know. When I say 2pn adiabatic invariant, I mean there has not been a complete analysis that includes all of the relevant post-Newtonian terms, allowing us to assess whether or not this will be conserved at higher order. I do not. So to the best of my knowledge, it is conserved at least at 2pn. We are in the process of comparing it with the results of numerical relativity simulations. As Sergei has probably showed you, right, there's two time scales involved. There's a secular effect, and there's oscillation effects. And so we'll try to have a more concrete answer as to whether or not this is robust in the strong field or not. So I can't say anything at this time. But when doing these comparisons, you have to take into account both the time averaging and the fact that this is only conserved at a fixed post-Newtonian order. So that's all I can say right now.
I was confused when you were showing your data analysis section. So you're referencing J and psi as natural coordinates.
Mm-hmm.
And I guess I can see how C doesn't really change even as the in-spiral progresses. But J is shrinking. So when you have these dots, presumably these are actual in-spirals that you have?
Yes. So. So this is the, and unfortunately I had to gloss over this since I wanted to show you some of the stuff at the end. Whenever we're estimating the parameters of a LIGO source, even whatever coordinates we use, we have to specify some initial data at some point. Rather than specify it at some arbitrary early frequency like 100 million years ago, which would be hard, we typically pick a frequency to which LIGO is sensitive, like 100 hertz. And that orbital frequency of, 2-2 mode gravitational wave frequency of 200 hertz. Of 100 hertz. And so therefore, this corresponds to the orbital total angular momentum of a system at that reference separation, or that reference frequency. And so this is well defined, and there are actually spin vectors associated with it that are also well defined. And I can show you a table of exactly what they are and give you code to compute them. But yes, this whole thing is constantly moving. So what does it mean to measure this quantity? It's we're measuring it. We're measuring a trajectory, and we're plotting a point on that trajectory. And you might be, when you bring up the point that you just made, you might be amazed that we can measure it so well. Because remember, this whole thing is during the in-spiral is moving that way. So we're measuring a tube of trajectories that at this particular reference frequency passes through this point. But we really are just constraining a trajectory tube and not some time varying quantity.
All right.